We'll get started. So yesterday we discussed till and we stopped after discussing um, or taking another look at the four fundamental subspaces, right? Uh, and we found that they were in fact orthogonal complements. Okay. Now we'll move on to another important topic, which will lead us to our next matrix decomposition method. The first one we saw was LU. When does this factorization exist? Any matrix? Triangular. What is, sorry, what I meant was, what is the condition on A? So we are saying A can be written as LU. I'm asking what is the condition on A for you to be able to write, express A equals LU. Right? So this is square, full rank, and no So that was the first of the matrix decomposition algorithms, matrix decomposition methods that we'll see in this course. Now we'll move on to another topic, which will eventually lead us to what is called the QR decomposition. Okay. Now, earlier we saw that if you have a subspace, right, and you have a vector B, and if we want to do orthogonal projection of this, we can do an orthogonal projection of this vector onto the subspace. Okay. This vector was B, and this vector is. Okay. And we know how to do this. We know that P is given by, let's say this is subspace S, the orthogonal projection matrix onto the subspace S multiplied by P will give me the orthogonal projection. Right? But how did we compute the orthogonal projection matrix? What did we need to compute the orthogonal projection matrix onto the subspace S? Okay. To compute it, you remember it was U transpose, and what were there? U was a matrix like this: U1, UR, where U, well, UI belongs to Rn, and R is less than or equal to. Well, for now, let's say R is strictly less. Sorry, not R. N. So, and what was special about the vectors U1 to UR? Remember? What is special about them? They formed an orthonormal basis for subspace S. Okay. So to compute the projection matrix, what we need is an to a sub onto a computer to compute the orthogonal projection matrix onto a subspace S. What we need is an orthonormal basis for that subspace. Okay. Now the question is, what if we don't have an orthonormal basis, but we just have a basis? Okay. This so if we have a basis, then if I have any arbitrary basis, can I generate an orthonormal basis using that arbitrary basis? Right. That's essentially the Gram-Schmidt orthogonalization procedure, where the goal is to convert an arbitrary basis to an orthonormal basis for the same subspace, of course. Okay. And the procedure is very simple. Now, let's say we start with a basis, x1 to xn, okay, where each xn or xi belongs to Rm. Okay. Because this is a basis, this is also linearly independent set. Okay. That's the definition of a basis. Okay. Now, we want to convert this basis into an orthonormal basis like this, whose span is also the span of B. That means it spans the same subspace. It's the basis for the same subspace. And the procedure for this is very simple. Let's do it geometrically first. Let's say I'm going to call the basis A. I'll not call it X, I'll call it A. Or have I used X? X, okay, I'm going to stick to X so that I don't confuse. So we have X1, X2, X, Xn. I'm going to stick to what is there on the slides. Okay. Xi belongs to Rm. The span of this will be some subspace. Okay. Now let's say we're talking about a one-dimensional subspace. Okay. That means the set that we started with is simply this. And we want to convert this to an orthonormal basis. Well, if there is only one vector, and if this is a basis for some subspace, one-dimensional subspace, that means x1 has to be non-zero. It's very easy to convert this into an orthonormal subspace. So orthonormal basis. Okay. How do you convert it into an orthonormal basis? Well, there is only one vector. There is no orthogonality condition that you need to check. The only condition you need to check is the vector that you have. Is it of length 1? If it's of length 1, then it's normalized. If it's only one vector, then it's an orthonormal basis. Then the way you ensure that you get an orthonormal basis from this, you take x1 and divide it by the second norm of x1. And I'm going to call that u1. You can verify that u1 transpose u1 is in fact 1. That's because u1 is x1 divided by x1 transpose. You can take the scalars out. Scalars will be square, and you have x1 transpose x1. This is nothing but the square of the Euclidean norm. So if you simply if you only have one basis set with one vector, the way you orthonormalize it is simply you normalize the length and make it 1, and that's it, you're done. This is if you have 1. Now the question is, what if you have 2? Right? Here we have to do a little bit more work. Okay? The first thing you do, so that means, so in the first case, right? Let me do the geometry first. If you're talking about R2 space, say we had a vector x1. The way you derive u1 is you ensure that the length of this vector is 1. So you divide, and then you get the span of u1 and x1 is the same. They'll span the same line, except that u1 has length 1, according to the Euclidean norm. That's the geometry. Now, if you had 2, we do the same thing. We take the first vector, and divided by the division operation is okay because we are always starting with the basis set. That means it's a set that is linearly independent. If it's linearly independent, none of the vectors will have zero length. The only vector that can have zero length is a zero vector. There can be no zero vector. Right? So we are guaranteed that the denominator will not be zero. Okay, at least the length of the individual vectors will not be zero. So this step is all right. So we've got our first orthonormal basis. Right? So let's say the two vectors were like this. This is U1, not U1. Let's say this is X1, this is X2. Okay. We obtain the first orthonormal basis vector by simply taking X1 and then normalizing it so that it has length 1. That's U1. Okay, let's assume this is unit length. Now, if you want an orthonormal basis, the second vector that you generate has to be orthogonal to U1 and it has to have length 1. Okay. The way we do that is, if you remember, when we do an orthogonal projection of a vector onto a subspace, right? So for example, if I asked you, can you give me the orthogonal projection of x2 onto x1 onto the subspace spanned by x1? How would you compute it? So we have a subspace that is spanned by x1, right? Now I want to orthogonally project my vector x2 onto the subspace spanned by x1. How would I compute? How would I do that? Geometrically, I would drop a perpendicular, and then this vector would be that orthogonal projection vector, right? So this one, starting from the origin. Okay. And how would I compute? I'm going to call this y1, y2. How would I compute y2? Well, how did we compute the orthogonal projection onto one-dimensional subspace earlier? You need to compute the projection matrix. To compute the projection matrix, you need an orthonormal basis onto the for the subspace spanned by x1. We already have an orthonormal basis for the subspace spanned by x1. That is u1. Right? So if I take u1 transpose and multiply it by x2, I will get y. But this is your projection matrix, orthogonal projection matrix. I'll get y2. Okay. Now, if you look at the difference between x2 and y2, right? That's this vector. Right? That's I'm going to call it E2. Maybe I shouldn't call it E2 because that's confusing. Sorry. I'm going to call it del2. I define the del2 vector as, that's this vector. And for sure, this vector will be orthogonal to y2 or u1. Okay. That means if I take del2 and divide it by the length of del2 and call that u2, then I'll get essentially this vector, or x1 and x2 were in this plane, y1 and y2 are in the same plane. That means the span of u1 u2 will be the same as span of x1 x2. And u1 and u2 are linearly independent because they are orthogonal to each other. That means now we have converted your original set of basis vectors, x1 to x2, to a new set which is actually orthonormal. And this is in fact an orthonormal basis. And the way we did that was we take the first vector, simply normalize it, and then we take the second vector, project it onto the subspace spanned by the first vector, find the difference, normalize the difference, we get the second basis vector, which is orthonormal, which together with the first basis vector forms an orthonormal basis. That's essentially the procedure. This is for 2. Now the question is, what do you do for 3? Same thing. You take the first vector, you normalize its length. Okay. What do you think we'll do next? Yeah. Take a guess. Well, same thing. You compute y2 from x2, which will be u1 transpose x2. You then compute del 2, which will be x2 minus y2, and from this you compute u2, which will be that's all. What about the third? So now we've got 1, 2. We need the third one. A, C. Well, earlier you had 2 vectors like this. You normalize the first one, and then you projected this onto here, on the difference, and that was the third basis vector, right? Now you have 3. You have 3 basis vectors, like 3 vectors like this. So you took the first one, normalized it, took the second one, did the orthogonal projection, and then found the second vector. You now take the third vector, project it onto the subspace spanned by the first 2, do the orthogonal projection, and the difference, so that will be some vector here. The difference will be this, and that is guaranteed to be perpendicular to your plane. And that, if you normalize it, that will be your third. Now, how do we do this projection of the third vector onto the subspace spanned by the first 2 vectors? Well, you need a projection matrix. How do you get the projection matrix? At least we've only seen one way to compute the projection matrix. What do you need to compute the projection matrix? You need an orthonormal basis. Do we have an orthonormal basis for the plane? We do. U1 and U2 are the orthonormal basis, right? So that means you now form a matrix U, which is U1, U2, and then you can compute Y3 as U transpose X3, compute del 3 as X3 minus Y3, and U3 will be del 3 divided by that's for 3. What if you had n in general? What do you mean by same? What will you do? Take the first vector, normalize it. Take the second vector, orthogonally project, find the difference, normalize that. Take the third vector, project it onto the 2-dimensional subspace, get the error, normalize. Take the fourth vector. Now you project it onto a 3-dimensional subspace, error, normalize error, and you keep continuing. Okay? And once you've gone through the entire procedure, what you will have is then a orthonormal basis for the same subspace that was spanned by your original basis x1 to xn. Okay? That's essentially the procedure that's described here. You can go through it later. Now, this procedure will work without any problems as long as the set that you started with was a linearly independent set. Okay. So, the only place where this entire procedure can run into problems is this normalization step, where you're dividing by stuff. Because if that denominator becomes 0, then you're in trouble. If you start with the linearly independent set, the denominator will never be 0. So you're guaranteed that way. If you don't have a linearly independent set, that means one of the vectors can be represented as a linear combination of the others. You are guaranteed that at some point you will have a divide by zero error, and that tells you that you have a linearly dependent set. So that means the Gram-Schmidt procedure is another way to find out if you have a linearly independent set. What is the first one? If I give you a set of vectors and I ask you, is this set linearly independent? Yeah. Well, you could do the Gaussian elimination. You could do the Gaussian elimination and see if any of the pivots go to zero even after you do row exchanges. If that happens, then for sure you have a linearly dependent set. If none of the pivots go to zero, then you have a linearly independent set. Okay? You can use the Gram-Schmidt procedure. You take a set, you go through the Gram-Schmidt procedure. If it goes through the procedure without a divide by zero error, then you know it's a linearly independent set. If you end up with a divide by zero error, then you know it's linearly dependent. So it turns out that you can express this entire procedure more conveniently in a matrix form. So let's say we started with a set of basis vectors like this, A1 to AN. Okay. You define matrices like these. Okay. U1 will always be defined as a zero matrix or a zero column vector. And then UI will contain as its columns the orthonormal basis vectors that you've already identified till then. Okay? For example, U1 will simply have capital U1 will simply have small u1. Capital U2 will have small u1 and small u2, and so on. So UI will have everything from 1 to I minus 1. Now, if you do this, right, you do this operation, that means you would have found the orthogonal projection of the vector x onto the subspace spanned by the first I minus 1 basis vectors. Okay? Because this is simply the projection matrix. Okay? That means you can find now the ith orthonormal basis vector by simply, so remember this is yi, right? So what you're doing in the numerator is you're doing xi minus yi. Okay? And the denominator is simply the normalization procedure. I mean, this looks complicated because it's some I minus, if you simply multiply x inside, it will be xi minus ui transpose xi. Ui transpose xi is the orthogonal projection. That's yi. That's all. So essentially, each time you add a new basis vector, this ui will keep growing. Okay, right. So that now brings us to the QR decomposition. So the QR decomposition says that a matrix A can be written like this, as a product of two matrices, Q and R. Okay. If A is full column rank, that means the matrix has to be tall or square. It cannot be fat. Okay. And these two matrices, in a way, special. This will be an orthogonal matrix. Okay. And if you started with a full column rank matrix, this will be upper triangular. So this says that any matrix A with full column rank can be written as a product of a orthogonal matrix and the upper triangular matrix. And it turns out that the elements of Q and R are simply stuff that comes out of your Gram-Schmidt orthogonalization procedure. Like in the case of LU, L and U were simply the result of the Gaussian elimination process. Here you have something that is the result of the Gram-Schmidt orthogonalization procedure. Okay. Now, let's say you start with a basis for some subspace. Okay. In fact, if you are talking about the vector space Rn, let's say I choose a basis for Rn, A1, A2, An, and I'll say this is a basis for Rn. Okay? That means linearly independent and spans Rn. Okay? Now, using this, I want to find an orthonormal basis for Rn. Okay? That means I want to find, I'm going to call the orthonormal basis Q1, Q2. And notice that AI and Qi are all elements from Rn. Okay. We know how to do this. If we simply apply the Gram-Schmidt procedure to this set, you'll get Q1 to Qn. So now if you put these basis vectors in a matrix like this and call that the A matrix, and this will be a n cross n matrix. Okay. It'll be full column rank because the columns of A form a basis for Rn. That means the columns are linearly independent. That means it's full rank. Okay. Full column, in fact, it's full column rank. It's also full row rank because it's a square matrix. Okay. And let's say we create another matrix called Q, which is essentially, this will also be a n cross n matrix. These are the orthonormal basis vectors that you identify out that computed from the Gram-Schmidt procedure. Okay. It turns out that both these would be related like this through a upper triangular matrix R. Okay. So here I'm essentially showing what the elements of the matrices will be. This is A, of course. This is Q, and this will be your R. Okay. But maybe that's too abstract. Let's just do the Gram-Schmidt procedure for one example, and then see how we can build this Q and R matrix. Okay. We'll keep things simple. We'll work with R2. Okay. These are the two vectors. Are they linearly independent? It looks like it, but let's do the Gram-Schmidt procedure and we'll find out. Okay, all right. How do we get, not you, I'm calling it Q now. How do we get Q1? How do we get Q1? What is the first thing you do? You take the first vector and normalize it. What is the norm of A1? It's not 2. Square root of 2. Right? That means you have 1 by root 2, 1, 1. You can verify that if you take the norm, the inner product of Q with itself, you'll get 1. Right? So that's our first. Okay. Now, What is the relationship between, I mean, this is trivial, but what is the relationship between Q and A? If I wanted to obtain A from Q again, I wanted to reverse the process, how would I obtain it? Yeah. Well, you simply multiply by root 2, or in general, this is root 2 in this particular case, but in general, what will this be? Yeah. Sorry. Norm of that vector. Let me call that R1. Okay. Let's go to Q2 now. To find Q2, well, we can't immediately directly find Q2. How do we find Q2 now? Sorry. Well, you take the second vector, you do an orthogonal projection of that to the subspace spanned by the previous vectors. The previous ones is just Q1. That means we take A2, we compute Q1 transpose. That will be the projection matrix. I'm going to call it P1. Okay. What will this be? Yeah, what is it? It's a column host multiplied by a row. What did you get? Yeah. See, I'm not good at lip reading, so you will have to be louder. Okay, all right. What do we do next? We find what we called as Y2, right? The orthogonal projection of A2 onto the subspace spanned by Q1. That will simply be P1 A2. Tell me what that will be. So it will be half 1, 1, 1, 1 multiplied by 2, 1. What will that be? Yeah. What is it? Okay, so it'll be okay. That's not enough. Next thing we do, find del 2. What is del 2? Del 2 will simply be the difference between the original vector and its orthogonal projection. What is this? Will be 2, 1 minus Okay. That means from this we can now derive Q2 as what? What will be Q2 now? Well, it will be del 2 divided by sum of del 2. What is that? Is half 1 minus 1 divided by. So this will be, it's your Q2. Okay. See, now the question is, okay, how do we reverse? If I wanted to reverse this operation, I wanted to get A2 back. What all will I need? So in the first case, we only needed Q1. In the current case, do we only need Q2? Well, if you only used Q2, you'd only get del 2. Okay, so let's do that. So if you use, you can get del 2 by okay, but what is del 2? Del 2 is this, right? Del 2 is some A2. Sorry. Yeah, here. But this is what we have on the left hand side is not A2, but this is well, I do see a relationship. A2 some have appeared here, right? I do have A2 and some other stuff, but I still have this Y2. Right? If I move that to the other side, I have A2, Y2 plus, right? But what is Y2? Sorry? Oh, it is B. Yes. Okay, that's fine. Let's do it step by step. We'll write it here. That was P1 A2 plus. But what is P1? P1 is Q1 transpose, right? That means Q1 transpose A2. Now, again, if you look at this, right, you can group these two. That's a scalar. That means you can bring it to the front. So I can write it as Q1 transpose A2 to Q1 plus. Let's say I call this R2, right? That means then A2 is Q1 transpose A2 Q1 plus R2 Q2. Okay. Since now I have both my equations. I have this this where I'm expressing A1 and A2 in terms of Q1 and Q2. Remember, R1 was simply root 2 here, but I will generally call it R1. And A2 is Q1 A2 multiplied by Q1 plus R2 Q2. Right? That means if I express these as columns of a matrix, I will have A1, A2, and I have Q1, Q2. Taking the column view of matrix multiplication, the first column, see, the columns of the left-hand side are a linear combination of the columns of the first matrix in the right-hand side, and the exact mixture for the linear combination comes from the columns of the second matrix. Okay? We know A1 is R times Q1 and it does not depend on Q2. That means the first column must be 0 Q2 and R1, right? Because this, if you do the matrix multiplication, A1 will be equal to R1 Q1. What about the second column? What will be the second column? Yep. The second column will be this scalar and this scalar. So this will be Q1 transpose A2 R2. Now, I don't know if we talked about what is an orthogonal matrix. Did we talk about it? Probably not. Okay, we'll come to that. This is our Q matrix, which is an orthogonal matrix, and this is upper triangular. Okay. The reason it comes out to be upper triangular is essentially as you go from A1 to AN, A1 only depends on Q1. A2 only depends on Q1 and Q2. A3 only depends on Q1, Q2, Q3. That's why you have the upper triangular shape. Okay. Now, if you simply extend this to higher dimensions, right? If you're dealing with n, if you started with the n cross n matrix, then you essentially have this. The Ri's are the scaling factors or the normalization factors, and everything above are simply terms that end up in front of each of the individual basis vectors. So again, you have Q. Okay, now, yeah, so, okay, let's do it numerically also, right? What will be the exact matrices here? What will be the exact matrices here? So A was 1, 1, 2, 1. What is Q? Q we've already identified, right? It looks like there is a 1 by root 2 here, so it'll be. What about Q2? Q1 is this. What is Q2? What is the R matrix? The first one is easy. First column is easy. What is the first column? Here. R1 is root 2. What about the second one? You compute it and tell me the elements of the second column. Well, we've already done the computation. You just have to figure out what the numbers are. What is R2? Well, the first element here will be Q1 transpose uh, A2. What is that? 3 by 2, is it? 3 by 2? What? 3 by root 2. Okay. What is the second one? No? What are you waiting for? We're just losing time. If you have the answer, you should just tell me. Do the right hand side and the left hand side match? Can you verify that if you multiply the right hand side, you do get the left hand side? Is it okay? Yeah. Okay. All right. Now, before we proceed, we'll just look at a few more uh, scenarios. Okay. The example that we looked at so far was full rank n cross n matrix. But I said, well, it doesn't have to be full rank. As long as it's full column rank, you're okay. That means a tall full rank matrix is still okay. You can still do QR decomposition. When we did QR decomposition and for the n cross n matrix, what is the shape of Q and R? What is the shape of Q? Yeah. Yes, it was n cross n. And the shape of R? Well, this has to be n cross n. See, I want you to start thinking logically. I mean, it's late enough in the course that these are things you should be able to compute, even if you're not immediately sure. This has to be n cross n. The first matrix is n cross n. So what should this be? N cross n. Okay. But what if I have a situation where A is n cross m is less than n, the rank of A equals, then the question is, can we do keyword decomposition? Well, it's full column rank, so we should be able to do. What will be the shapes of the different matrices? This is, of course, n cross m. Yeah. Sorry. The first one is n cross n. Okay. Okay. That's possible, right? But let's see if that makes sense. What are the columns of A? Well, original set of linearly independent vectors that you started with. What are the columns of Q? Well, how did you get Q? Well, we did Gram-Schmidt orthogonalization procedure and we got Qs. What can you say about the number of elements in A, and number of basis vectors that you started with, and the number of Q vectors that you derived? They will be equal, right? If there are n, if you started with m A vectors, you will have m Q vectors. That means, what can you say about the shape of Q? It cannot be n cross n. Okay, let's revise that answer. This is wrong. So most likely this is also wrong. What will be the shape of Q? N cross m R. So if you started with a square matrix, you get Q and a triangular matrix. If you started with a tall matrix, you get a, I'm going to draw it like this. You get a square Q, you get a tall Q, and you get a small upper triangular matrix. Okay? This is when you have full column rank. Okay? Let's say you decided that you're going to be a little bit more lenient with your Gram-Schmidt procedure and say, okay, I can, if I start with a linearly dependent set of vectors, one of the denominators can go to 0. Let's actually do an example. Otherwise, it will probably still remain very abstract. I'm going to keep it 1, 1. One, one. Let's do the Gram-Schmidt procedure and tell me what is Q1. What is Q1 now? Yep. So it'll be 1 by root 2, 1, 1. Great. Now let's find out Q2. What do we do? This is the first step. What do we have to do to find out Q2? Find the projection matrix. And then from this find Y2. From that find del 2. And then from this get Q2. You tell me what you find. Have you found out P1? Okay. What about Y2? Same as what? Say whatever you have. It's okay if you're wrong. Say whatever you have. What is it? Y2 cannot be 0. Are you saying del 2 or Y2? No. What is P1? Okay. P1, man. See, yeah. P1 is a projection matrix, right? How did you get 1, 1 if you multiply the column vector with the row vector? Here. It will be 1 by 2, 1, 1, 1, 1. This is what you should have got. Okay? That means Y2 will be, what do you get? Yeah. 1 by 2, 2, is it? What is A2? Y2 is simply A2. So what will be del 2 now? Be there. Now we are in trouble. We cannot divide anymore by 0. We cannot normalize. Why did that happen? Yes, it turned out that way because A2 is a is simply a scaled version of A1. That means they are linearly dependent. That is why you got 0 here. Well, you could say, okay, so what? Okay, I'm going to still try and write A1 and A2 in terms of Q1 and Q2, which you can do, right? A1 is simply what? Root 2 times Q1 from here. What is A2 now? Well, there is no Q2 anymore. You only have one basis vector. How is A2 related to Q1? It's kind of a trick question. Simply have Q1 plus Q1 is 1. Okay, so I can write it like this. I can write A2 like this. Okay. If I move stuff around, I can write this as Q1 transpose A1 into, sorry, A2. Okay. That means now, because it's a linearly dependent set, both A1 and A2 only depend on Q1. Okay. That means now my QR decomposition is going to be slightly different now. There is only one orthonormal basis vector that I've got, right? So my what is this? Q1 transpose A2. This will also be 0 because it does not depend on, there is no Q22. Sorry, no, this is wrong. See, you should have got it. This will simply be root 2 and this will be What is Q1 transpose A2? Essentially this. Okay. So if you in Gramsci orthogonalization, if you started with a linearly dependent set, okay, if you started with n vectors and there are only r linearly independent set of vectors, then the number of q's you can obtain is only r. Okay? That means even though you started with the n cross n matrix, you will only have a n cross r matrix, and your r matrix will be r cross n. Okay? Another thing to keep in mind is what would happen if you change the order of your columns? Will you get the same QR decomposition? Will you get the same Qs first of all? Here, instead of choosing 1 1 as A1 and 2 1 as A2, what if I had chosen them the other way around? If this was 2 1, right, then the basis vectors that you'll get will be completely different. So the order also matters in QR decomposition. Okay? Just because you started with the same set of vectors, if you use different orders of these vectors in your QR decomposition, in your Gramscian procedure, the two of you will come up with two different bases. Both of them will be orthonormal and they will be the basis for the same subspace, but just they are different orthonormal bases. Okay. Now, we will first talk about orthonormal or orthogonal matrices before we proceed. Okay. It's very simple. If a matrix A, a square matrix, we say it's orthogonal if that's all. Okay. If the inverse of the matrix is simply A transpose, then it's called an orthogonal matrix. The nice thing about the orthogonal matrix is an orthogonal matrix A. So you have A1, A2, AN. Here, if you take any AI and you take the transpose of that column with itself, okay, this will always be 1. That means the columns all have length 1 according to the Euclidean norm. Okay, and if you take the inner product of any column with any other column, it will be 0, which essentially means that if you have a square matrix A which is orthogonal, the columns of the matrix form a orthonormal basis for Rn. Means if you simply take an orthonormal basis for a vector space and you put them as columns in a matrix, that matrix will be an orthogonal matrix. Okay? The same is true about the rows as well. The rows also have length 1, and the inner product of any row, any other row is 0. You can extend this idea to tall matrices as well. You can have tall matrices with, if I remember correctly, I think the definition of orthogonal matrices is only for square matrices, but you could have tall matrices which satisfy at least the first property. The columns, so if you have a tall matrix like this, and you have columns, okay, the columns could all have, let's say I call this matrix B. The columns could all have length 1, and the columns could be all mutually perpendicular to each other. Okay. In that case, the columns of this matrix will form an orthonormal basis for the column space of that matrix. Okay. So when we talk about this, when A is square, then Q is an orthogonal matrix. If it is not square, I'll have to check this. If all matrices that satisfy whose columns form an orthonormal basis, they are called orthogonal matrices as well. I'm not sure. Okay. See, earlier when we could write LU, we said if you have the LU decomposition, then solving X equals B was very easy. Okay. It turns out if you have this, then solving this is also quite easy. Okay. Because if you had the QR decomposition, then AX equals B can be written as QRX will be equal to B. We can move Q to the other side, take the inverse. But the nice thing about this inverse is the inverse is simply the transpose because it's an orthogonal matrix. That means you now have Rx equals Q transpose B. This is a relatively simple operation to do. And remember, R is a upper triangular matrix. That means you can solve for X by simply through substitution. Okay. That is all I wanted to say for orthogonality, and that's the end. Again, there is probably a lot right now, but I think you guys need to go and practice a little. I don't know how much you're actually practicing with numerical examples. Initially, I would focus on the numerical example. How many Gaussian elimination examples did you try on your own? You simply made up a matrix and then you tried to do Gaussian elimination. And then maybe then check with Python or MATLAB to give for that matrix, give you the reduced to echelon form and made sure that what you got was correct. How many have you tried like that so far? 3 is not enough. You have to do enough to a point where the Gaussian elimination procedure is now completely ingrained in your brain. That you know all the steps. You should be able to do it in your head. You do the same for QR. Once you do that, once the steps are clear, then maybe what they mean, how they connect to each other start to become clear. If you don't do that, it's hard to get there. More practice is the way to go. So for example, you should not be taking so much time to compute norms, multiplying matrices. Doing a blunder of not being able to do outer product at this stage of the course is a big problem because the rest of the course will only get harder after this. Okay, if you're not able to do that, go back. If you have to do 100 problems of computing inner products, outer products, lengths, different norms, multiplying matrices, doing Gaussian elimination, doing QR decomposition, you sit and do it. There is no other way way out of this. Okay, okay, sure. We'll stop here and then we'll. I'm not here for the next 1 week. We will again meet on Thursday, next Thursday.